Hello everyone, so welcome back. So we have been discussing about assembly language and we have seen few aspects of assembly language, why it is important, why we should learn about assembly language. We try to motivate ourselves. Followed by that, we looked into different machine models. Now these machine models actually determine how the assembly instruction will look like. So we looked at stack based machine model, we looked at accumulator based machine model, then register and register memory machine models. Now depending on which machine model we are looking into, the number of operands, explicitly mentioned operands will vary. But for all our course discussion, we will be primarily focusing on register machine model. So basically all the three operands will be explicitly mentioned and we will go with that register model for most of our discussion. All right. So continuing from there, we would today like to look at the registers, what kind of registers we have, and more closely we will look into the memory and how this data, different data or instruction can be stored in the data memory and as well as can be read from the memory. So that is what we will first look at, and then we will be looking into basically different arithmetic operations, and also look into a toy assembly language for a very simple ISA, which the textbook calls simple RISC ISA. So we will follow the same and it will help us in understanding the assembly better, so that we can later on use this understanding to write let us say assembly code for other processors. All right. So let us move into that. So we will start with understanding the different registers. Now these registers, we have seen that or we have discussed that since the main memory, accessing the main memory from the CPU is time consuming, so we would like to have some registers which are very close to basically your CPU, and they can be accessed in a very efficient and fast manner. So now these registers are also can be very simply mentioned as named storage locations. Named storage locations. Generally, the different processors will have few general purpose registers. So these general purpose registers generally vary from any number between 16 to 32 or even 64. In case of ARM, generally it has 16 general purpose registers, and these registers are named something like from R0 to R15. All right. Similarly, MIPS or the other RISC processor has 32 general purpose registers. They are also named from R0 to R31 and so on. There can be some specific registers which are primarily used by the machine, which can be machine specific registers, for example, which are used for controlling different or storing different control signals, how the power control settings will be stored, then the speed at which, let us say, the cooling system should work at different activity level, etc. So those things are stored in machine specific registers, which are also basically MSR, machine specific register. And then there are some registers which has very specific functions. For example, stack pointer. So, stack pointer is a very specific register which has this function of pointing to the top of the stack. Then we have already seen program counter. Program counter is another such example. Then return address register is also something which is very commonly can be seen. So, this return address register is the register where you store the return address when you go for serving a subroutine. All right. So, these are specific registers or with special functions, basically we can say them as special register. All right. Now, coming back to basically how this data or this content, whether it is instruction or memory, is stored in the memory. So, one very simple way to visualize this is that let us imagine that our memory is nothing but a long array. All right. So, basically it is a large array of bytes, and let us say this each of these elements in the array can store a byte, all right, or each location this block can store a byte, and I can also specify the address of this location. So, basically each location has an address and each location can store a byte. So, the first address is let us say 0, and if we increase the address by 1, then we point towards the next location and so on. All right. So, the program is stored in some part of this array, and the program counter actually points from where to where you have to, basically how you should read the instruction one by one. So, program counter, as we know, stores the address of the current instruction that need to be executed. So, this is our simple way of looking at memory. Now, how to store the data in memory? So, we have seen that data can be of different types. If you look at any high level language, you must have specified that, okay, so let us take the example of C. So, you will have a data type called character. So, generally it has 1 byte length. Similarly, you have short, which is 2 byte. You have integer, which is 4 byte, and long integer, which is 8 byte, right. Now, if you let us say if you have an integer that needs to be stored in the memory, then now there are two ways you can store the data in your memory or that integer in the memory, and these two ways are basically very simple. Let us say I have this 4 bytes, so and I have this memory location, so where I can let us say store this integer. This is the let us say lowest address n, and this is n plus 1, this is n plus 2, and so on. All right. Now, I need to store this 4 byte, one location can store 1 byte. Now, if I store the MSB here, so out of this 4 bytes, so the most significant byte, if I store it here, then the next most significant bit, and so on. This is one way of storing the data. Other way of storing the data can be I store the least significant byte here, followed by the next byte and next byte. So, depending on how I store the data, basically whether I store the MSB in the lowest location or the LSB in the lowest location, basically I can store my data in two ways. So, the method or so these are just conventions or protocols. So, the protocol in which the MSB is stored in the lowest location, that is called big endian. So, this is called big endian representation. So, again these are also specified in the ISA. So, basically what it does, it stores the MSB is stored in the lowest location. The opposite is called little endian. Here the LSB is stored in the lowest location. All right. So, pretty simple. Now, what are the examples? For in case of little endian, your ARM, then x86, these ISAs follow the little endian representation, whereas if you look at IBM PowerPC, then SPARC, Sun SPARC. So, these uses the big endian representation. All right. So, I guess if we look at a very simple example, it will it's very, very intuitive, but still I can quickly show you. Let us say I have a binary number, so basically which is represented in hex. So, 87654321. So, I have this basically 4 bytes that need to be stored. So, in case of big endian, so the storing will be done, let us say this is my basically lowest address. So, in case of big endian, the MSB will be in the lowest location. So, this is how it will be stored. In case of little, so in case of little, so you will be doing the opposite. So, basically your LSB will be stored in the lowest location. All right. So, I guess this is easy to follow. Okay. Now, similarly we can think of storing an array. So, if I need to store an array, single dimension array, so the array will be, each of these array elements will be stored one after another, and depending on what is the size of your integer, let us say each array element will contain an integer and an integer requires 4 bytes. So, your address will be updated accordingly. So, for example, if I have an array of size 100 elements, then like how I will store them. So, I will store them, let us say the first element of the array will be stored in the first location A0, then I will have 4, the next location will start at after 4 bytes. All right. So, this is where my next array element will be starting, and it will take again 4 bytes and so on. All right. So, I hope that makes sense. Now, how about two-dimensional arrays? How do we store two-dimensional arrays? Because we need to deal with two-dimensional arrays very frequently, right? So, if I have a two-dimensional array, let us say I have an array, integer array, which is defined as basically 100 by 100 array. So, in that case, I have again two methods to store this data. So, what are the two methods? So, the two methods are called row measure and the other one is called column measure. So, I am sure many of you are already familiar with basically C, Python, they uses row measure strategy or row measure technique for storing the two dimensional data. So, in case of row measure, as the name suggests, it is very intuitive. So, basically the first store this let us say this is your two dimensional array. So, what you will do, you will take the first row and that first row will go into your array first, followed by that second row. The second row will go here, followed by that the third row and so on. So, basically you will read row wise, alright. So, you will read one row at a time and then you will store it in this one by one. Now, in case of column measure, basically MATLAB, Fortran, so these languages uses column measure. So, in this case what you will do, you will read the first column that will be stored in your array, followed by that second column and that will go into the next and so on. So, basically you store the first column in an 1D array, followed by the second column and so on. So, these are few things which we should be aware of, like these are defined by your ISA. All right. Now, we have already seen that depending on the machine model, our instructions basically will have the structure of a assembly level instruction will have structure of an instruction or structure of this instruction will be basically the opcode followed by their operands depending on how many of them you need, operand 1, 2 and so on, alright. Now, these operands can be, as we have seen already, the operand can be a constant number. For example, if you are doing directly manipulating some number, for example, you are adding let us say the content of a resistor with a direct integer value. So, that in that case the operand can be constant and this constant is also known as immediate. Alright. The operand can be register or the operand can be memory location. Alright. So, we have already have seen this. So, a few examples of our example can be, let us say, any operand add, then R3, R1, R2. So, that means you add the content of R1 and R2 and store the value in R3. Similarly, you can have other operations like multiply and so on. All right. So, this is what our instructions will look like. Now, the instructions can be of different types. All right. So, what are the different types we can have in the instruction? So, the instruction can be of type let us say this okay, let me just write it down, types of instruction. So, the types of instruction can be data processing instruction or basically arithmetic instructions. So, what are the data processing instructions? You can have instructions like add, subtract, multiply, divide, compare. Then the other logical operations like AND or so basically logical operations. Similarly, there can be instructions which are dealing with the data movement. So, data transfer instructions. Data transfer instructions. So, basically these are load store kind of instructions. So, they are used for transferring values between registers and memory location. So, load, store, etc. There can be branch instructions. So, basically you can branch to a different location if you need to, if the program flow needs to go there. Then there can be some special instructions like so if you need to interact with the peripheral devices or basically you need to specify some flags, etc. So, there can be some special instructions. So, okay. Now, we have already seen that depending on the machine model, you can have different number of operands or different operands explicitly mentioned. The other thing which we will be looking at more closely is the addressing mode. Now, we talked about data transfer, etc. Now, how do we specify that address and how we get the data and all these things, that is determined by addressing mode. So, we will talk about addressing mode in a minute. Now, there are simple notations which already we have seen multiple times. So, when we write down something like this, that means that we are trying to basically put the content of R2 into R1. Similarly, basically transfer the content of resistor R2 into R1. Similarly, if I write something like this, that means so there is an immediate value. So, basically what we are saying that add 4 to the content of resistor R2 and then this content, the total content is transferred to the resistor R1. Now, there is one notation which we may not have highlighted, we might have used, but have not highlighted, is this. What does this notation means? This notation means that you access the memory location that matches with the content of R2. So, basically the content of R2 is specifying an address. So, you read the data in that address and store the data in register R1. So, basically access the memory location that matches the contents of R2, and then you store the data which is there in that address in register R1. All right. So, these notations will become handy when we discuss about addressing modes. So, let us come to addressing mode and discuss what are the possible addressing modes we can think of. So, this is also very important, and the ISA specifies what kind of addressing mode the machine can handle. So, the first addressing mode we will talk about is called immediate addressing mode. So, basically as the name suggests, the address in immediate addressing mode, the address is specified by some immediate value. All right. So, basically let us say we have an operand A, and we want to store a value or basically we want to initialize this operand. All right. Now, one way to initialize this operand is basically you directly give the address. For example, let us say the address where from the value should be taken for initializing the variable A is directly mentioned here. So, the address can be, let us say, depending on how many bits you have for specifying the address, you can have a hex address which is let us say if you are specifying 8-bit address, then you will have something like this. So, that is an immediate value which tells that where from you should update the value of A. So, this is your immediate addressing mode. So, basically you are directly giving the address in the instruction itself. Then there is something called Resistor Direct addressing mode. Resistor Direct addressing mode. So, now again let us say we want to initialize the value of A. So, we can specify that this is the address from where you have to, or this is the register from where you have to get the value of A. So, this is a Resistor Direct addressing mode. So, you are getting the value from the register itself. Now, there is another mode called Resistor Indirect. Now, there so, in case of Resistor Indirect, you will update the value of A with the content of this basically the content of this register will specify an address, and you have to go to that address and get the value, and that value is what you want to update this variable with. So, if we pictorially want to see how the resistor indirect mode looks like, so basically let us say this is R1. So, this is your register file, right. So, you have a bunch of general purpose resistor and R1 is here. So, this is my register file. Now, this content of R1 will basically point to a location in the memory. So, this is my memory. So, let us say this is the location which it points to, and this content, this is the value which I want to basically update my variable A with, alright. So, this is what we mean by resistor indirect. Resistor direct, you directly get the value from R1. Resistor indirect, R1 basically points to the address from where you have to get the value. I hope this makes sense. There is another interesting okay, sorry, I do not remember exactly how I said this. So, basically this immediate addressing mode will get the value directly in the instruction itself. So, this is the value, this is not the address. So, in immediate addressing mode, you directly update the value to the variable you want to update it, alright. So, resistor indirect we have seen. Now, let us look at base offset addressing mode. So, this is very useful one. So, let us say I want to update the value of A, and I will be using a resistor, plus I will also have some offset. So, what it does, it starts with very similar to what the resistor indirect addressing mode is. So, basically you will look at the value of R1 that will specify the so with this value of R1 you will be adding the offset to get the actual address, and this total address is basically where from in the main memory you have to get the data, alright. So, this is your value, this is memory. Now, this is very important, because let us say you want to access an array. So, you had values of an array stored in this memory, and you know that the array starts from somewhere, let us say some location like n, alright. So, let us say you will store the value of n in R1, and you know the content or each or the array is containing let us say integer values, and integers are represented using 4 bytes. So, the first element of the array is denoted or located by this value n, which is stored in R1, and in this case offset will be 0. The next element of the array will be at n plus. So, basically let us say if this is my array, so first element is stored in here, next element will be, so it will require 3 locations to store the first element, the next location will be n plus 4, that is the starting point of the next element, and followed by that the third element will be at n plus 8, and so on, right. So, you see that here this 4, 8 are nothing but my offset. So, I can very well update my offset to to access the subsequent elements in the array. All right. So, this becomes very useful. So, this is called base offset addressing mode, and typically the way the instructions are represented, for example, let us say I want to give you the syntax. So, basically it looks something like this. So, let us say you want to store some value. So, store, let us say some resistor R4, and you want to store it with let us say the offset value is 10. So, you will write the instruction like this 10, and let us say the resistor is R1. So, 10 R1. So, this is the syntax, or this is how the addressing mode looks like. So, we will look into it more closely in our subsequent discussions. So, this is the offset value and this is the resistor value. Similarly, there is addressing modes like memory direct. So, where you specify the address directly. For example, let us say again I want to update A, and I will be specifying the address here, memory address itself. All right. So, this is called memory indirect. There is another interesting and useful addressing mode called PC relative. So, this is very much like the resistor, basically base offset mechanism, but here the resistor we are talking about is the PC. So, basically PC plus offset, especially when you need to do lot of let us say you need to take care of lot of branching instruction, etc., and you want to do different kind of operation relative to the PC, then it becomes very useful. So, these are the different addressing modes which are useful ones. We will be looking at in our subsequent discussions. Now, so to summarize, we can look at the different real world instruction sets and different things we have discussed so far. For example, the machine model, the number of explicitly mentioned operands, how many memory access, etc., are happening, the number of general purpose registers, the number of bits which are used for addressing, and also the typical use of these processors. If you see, you will see that now we have listed almost all popular architectures and their ISAs here. So, for example, alpha is one very famous ISA, which is basically the machine model is resistor. It has 3 explicitly mentioned operand. It is a 64-bit machine, and there are 32 general purpose registers, and typically it is used for workstation kind of applications, and the address size is also 64-bit. Similarly, you can look at ARM. The machine model is resistor, 3 operands, 3 explicitly named operands. The operands cannot be memory, and then the data size can be either 32-bit or 64-bit. It has 16 general purpose registers, and then the address size can be also 64-bit or 32-bit, and generally widely used in cell phones, embedded systems. MIPS again very similar. So, Spark you can look at. So, again this is this has similar kind of machine model and the number of bits, etc. The DSP processor by TI C6000 is a resistor processor and specifically used for DSP applications. Similarly, you can look at IBM 360 and basically so then basically you have x86, so it's a register memory, and IBM 360 is also register memory. So basically one of the operands can be memory, and that's what you can see here basically in the number of operands and memories as well, and other things you can look for yourself. So these are details about how the different ISAs are designed and how they impact the design decisions based on the things which we have looked at so far. All right. So I hope the discussion so far has made sense to you. So what we have looked at? We have looked at the machine models, which determines the number of explicitly mentioned operands, whether the operands are coming from register or memory or some immediate value, etc. The addressing modes we have talked about. We have talked about the general purpose registers and things like that. So now after this we will go into looking into a looking into some of the examples, and basically we will look into an ISA which we will be exploring and we will be building on our own. So this ISA, as the book names it, as simple RISC. So basically it's a RISC ISA, and it will be very simple to implement and understand, and it will help us in understanding the ISAs, basically the other ISAs, and accordingly it will help us in writing assembly codes also for those ISAs. So let's come back to our pen and paper mode. So let's say this simple RISC. So we will build this simple RISC processor, and we will write down the instructions for them. So basically, to start with, we will go into we will start looking into some of the simple instructions which an ISA should have, and from there we will look how can we make it more and more basically complex. All right. Okay. So in our simple RISC, we will have 16 register. All right, very much like ARM, and these registers will be numbered from R0 to R15, and let's specify that R14 will be a register which will be doing the task of stack pointer. So basically it's a special register will be used for stack pointing. All right. Then we will have another register R15, and this will be used for return address register. All right. So we will call it RA, and this is SP, stack pointer and return address register. The memory we will be considered as von Neumann model. So basically the data and instruction memory are basically together, one large array of bytes. That's what our memory is. We will have special flags. We will have a special flag register as well, and this flag register will contain the results of the results of the comparison outcome. So, let us say we will have a instruction called comparison and compare, and depending on the outcome of the compare, so there will be two flags, basically flag flag dot e equals 1. So, basically if the comparison outcome is equal, then we will have this flag dot e as 1. So, it will show us equality. The other flag is flags dot gt. So, basically it is, if it is 1, that means the outcome of the comparison is greater than. So, basically if let us say I write down compare R1 R2. So, if R1 is greater than R2, then this flag will be set. So, we will talk about those instructions in a bit. Now, what kind of instructions our simple RISC should have? So, we can start with very basic instructions like the data movement instructions like move. So, basically the instruction move R1 comma R2 implies that the value of R1 basically the value of R2 should be loaded into R2. Similarly, if I write move let us say R1 with an immediate value, then it implies that that R1 should be loaded with this immediate value 3. Okay. Now, what should be the range of this immediate? Now, in our simple RISC, it has 16-bit immediates. So, if it is 16 bits, then you know in 2's complement the range of immediates can be minus 2 to the power 15 to 2 to the power 15 minus 1. So, that is the range of immediates that can be handled by our simple RISC. All right. So, I hope these things are absolutely clear. Then we can look at a bunch of arithmetic instructions. So, arithmetic and logic instructions. So, let's list down all the arithmetic and logic instructions. So, basically you will have add, subtract, multiply, division, mod and comparison or compare. So, for example, add instruction can be, let us say add R1, R2, R3. So, that means you add the value of R2 and R3 and store it in R1. Similarly, you can have an add instruction where one of the operand is an immediate value. All right. So, the meaning you know already. So, here basically R2 plus 10 will be stored in R1. Similarly, you can have subtract, which basically let us say R1, R2, R3. So, it means that you subtract R2 from R3 and store it in R1. You can write down multiplication, again R1, R2, R3. That means R1 will be storing the value of this operation R2 multiplied by R3, right. Now, in case of division, so again R1, R2, R3. So, in case of division, you will be storing the division, basically this result by dividing R2 divided by R3, and you will be only storing the quotient here. All right. For the remainder, you have to perform this operation mod. For that you have the mod instruction. So, basically it will store in R1 the value of R2 mod R3, which is the basically remainder. Similarly, we have this basically compare instruction. So, it compares R1 and R2, and accordingly it will set the flag. Now, if R1 and R2 are equal, then it will be setting this this flag, until you do not perform any other comparison instruction, this flag status will remain as it is. If R1 if the R1 is greater than R2, then this flag greater than will be set. All right. So, this is how basically our move and arithmetic and logic operations for this simple RISC ISA will look like. All right. So, now let us look at few examples and try to write down some assembly codes for our completeness. So, let us say I have a task at hand, and the task I have is basically I want these variables, basically a equals 3, then b equals 5, and c equals a plus b, and d equals c plus c minus 5. So, I want to perform this task using my simple RISC. So, how should we proceed? So, basically the first step you have to do is basically you have to store these values of a, b, c, at least a, b and c, even d, into some registers. So, so you can do first this operation. So, a is in stored the content of so, first thing you need to do is basically you need to move the value of so let us say a represents R0, similarly b represents R1, c represents R2, and d represents R3. All right. So, I can write now instructions like move your R0, which is a, with the immediate value 3. Next, move your R1, which is basically the variable b, with the immediate value 5, and then you do this add operation, where you store the value of this add operation into R2, and what are the variables you should add? You add R0 and R1. All right. So, R2 is already associated with c. So, c is stored with the value of a plus b, and then you subtract and store the value in R3, and you subtract 5 from R2. So, this is your assembly code. So, this is very simple, nothing very complicated. Similarly, we can do other operations. Let us say if you have a multiply, if you have a mod operations, etc., all these things we can do, right. So, I will leave it to you guys to try these things. I can show you one example of compare operation. So, these are interesting arithmetic operations. So, let us say you want to compare. So, this compare the values of 3 and 5, and you want to print the value of the flag. Basically, what will be the status of the flag register? So, what you can do, you can think of assigning this. So, these is more like little high level language. So, basically you assign a variable for this number 3, assign another variable for number 5, and then you write compare A and B. Now, in assembly how you can write this? Basically, you have to load these values of A and B in some register. So, basically you will be moving R0 with 3, move your R1 with 5, and then you write down basically CMP compare R0 R1. Now, since R0 is less than R1, so what will happen? You can look at the status of flag flags dot e. It will not be set because the values are not equal. Similarly, flags dot gt greater than will be also 0 because R0 is not greater than R1. That is why both these flags will be 0. Now, if you do the other way around, let us say you change R0 to 5 and R1 to 3, then when you do this comparison, then the greater than flag will be set. Similarly, you can make both of them equal, and in that case the flags.e flag will be set. I hope these things are pretty straightforward and intuitive. So, you will be able to you will understand that easily. Okay. Similarly, let us say we can try few more examples. Let us say I want to do this compute operation. So, compute, let us say 31 divided by 29 minus 50, and you would like to save the result in R4. Okay. So, the assembly level language code you can write down. So, you have to first move let us say to some variable R1 this immediate value 31, move R2 with the next value 29, then you do this division where the result is stored in R3. So, R1 divided by R2 and the result is stored in R3, and then this is the result you get, and then this result need to be basically 50 needs to be subtracted from this result, and that should be stored in R4. So, basically R4 equals R3 minus 50. All right. So, that is how you will write the assembly code to get this operation done, get this computation done. All right. Similarly, you can look at logical instructions. So, basically the AND OR kind of things, AND or NOT operations. So, these are generally bitwise operations. So, for example, logical. So, for logical instructions, so let us say you write down something like this, and R1, R2, R3. So, what it will do? It will perform the AND operation between R2 and R3 and store the value of value in R1. So, let us say now let us say your R1 is a number 1010, R2 is a number which is say 0110. So, when you say this AND, so this is a bitwise AND operation. So, basically it will do this AND operation. So, R1 and R2 will be basically 0 and 0 is 0, 1 and 1 is 1, 1 0 is 0, 1 0 is 0. So, this will be the outcome of your AND operation. Similarly, you can look at OR, NOT and so on. All right. So, I think these are straightforward things. The other instruction, so we have looked at arithmetic move, data movement instruction, then we have looked at this logical instruction. The other instruction which is very handy is called shift instruction. Alright. So, there are basically different types of shifts. So, for example, logical shift left, let us say. So, logical shift left, as the name suggests, and the operator is denoted as this, alright. So, let us say you want to logically shift this 4-bit number to left by two positions. So, what this number will look like after you shift logically? So, it will be looking like this 1, because this 1 will be moving on the left side 2 positions. So, 1 0. So, this is your number, and the positions which are basically now because of the move shift operation, these positions are empty. So, you will be putting zeros in those positions. So, that is your logical shift left. Now, you can look closely and you will realize that this shift left operation is same as so, if you shift left by n position is same as multiplying by 2 to the power n. Right? So, this is very handy, because you know that multiplication is a very expensive hardware wise, it is very expensive, time consuming, etc. So, if you can avoid multiplication by this shifting only, then it is very useful. And I do not think you need to we need to basically explain why shifting right shifting left is equal to multiplying by 2 to the power n, because it is very intuitive, right. So, if you multiply something by 2 to the power n, you will see that it basically is equivalent to shifting left by this n points. Similarly, there is logical shift right. So, okay, by the way, the logical shift left, the instruction will be like this, LSL, logical shift left, and the operator will be denoted by this less than signs. Okay. Now, there is for shift right, there are two options. One is logical shift right, another is arithmetic shift right. Okay. So, let me just talk about arithmetic shift right first. So, arithmetic shift right, or ASR, the operator is basically this, all right. So, let us say you have this number 1101 and you want to shift right one position, and it translate to 0001, right, intuitive. Now, if the number is this, and if you want to shift two positions on the right, then in case of arithmetic shift right, this will be treated as sign bit. So, these are for basically signed numbers. The arithmetic shift operation is for signed numbers. So, in this case, when you shift two positions, so your number will now become basically 0 1. So, this is what the shifted number looks like. Now these two positions, they will be same as your sign bit. So basically you have to replicate the sign bit. Okay. So this is your arithmetic shift right operation, and this operation is same as dividing a signed number. So basically same as dividing a signed number by 2 to the power n. You can verify this if now similarly there is a logical shift right. So in logical shift right you basically deal with unsigned numbers. So now the operator here you have to be very, very careful. So here you will have 3 greater than signs to indicate the logical shift right operator. Okay. So if I have a number like this and I want to do logical shift right, so the number will translate to basically 0 0 1 0. All right. So it's same as dividing the unsigned number or unsigned representation by 2 to the power n. All right. So you can take few examples. For example, if you have a assembly code which says that LSL R3 R1 R2, so what it will do, it will store the value in R3 for the operation where R1 will be logically shift left. So but by how many position? By R2 positions. Okay. Similarly you can look at few more examples. All right. I hope this makes sense. Similarly, if you have arithmetic shift right, then you will be writing ASR here, and pretty much it will look same, only the operator will be different, and logical shift right you will have this 3 greater than signs as the operator. Okay. All right. So now using this shift operations we can do very interesting stuff. For example, you want to, let us say, compute. I am just giving you quickly some overview. Let us say you want to compute a number 102 and you want to multiply it with 7.5. and you want to do it with the shift operation. So can you think of how we can do it? So what we can do, so let us say we write down that okay, we will first move this value 102 into the register R0. All right. Now the first step we can do, we can multiply this number 102 with 8. Now multiplying this with 8 is equivalent to shifting this number to the left by 3 positions, right. So we can write down LSL R1 R0 3. So what it will do? It will shift the content of R0 towards the left by 3 positions, which is equivalent to multiplying it with 8. The next thing we will do is basically take this number and shift it towards your right by one position, which is equivalent to dividing it by basically dividing it by 2. So, L S R, R2, R0 and 1. Now, so what we have done, so in R3, let us say we want to store the final result. So, this is 102. So, we have multiplied the number with 8 first, and then we have multiply it with half, or we divided it by 2. So, now if I subtract these two numbers, so equivalently what I will have is this. This is nothing but what I wanted to compute, right. So, if I now subtract and store this result in R3, and what I will subtract R1 and R2, then I should get this result. So, now you see that without doing any multiplication, any floating point operation, I could get this result by just shifting operation. And if you look at the performance of this shift operation is much faster compared to your multiply or division, as you can intuitively think. So, that gives immense performance. So, that is why if we can somehow convert our multiplications and divisions by shifting operations, it gives you huge advantage. So, we will try to see some basically in our exercises and in our practice problems also, we will try to see how we can exploit this kind of strategy for doing multiplications or divisions more efficiently. All right. Okay, so I will stop here at this point.